My name is Madeline Lasias, and I'm currently an almost complete PhD student at the University of Cambridge in the Department of Computer Science and Technology. Today, I'm going to be sharing about Tessera, which is our open source geospatial foundation model. Before I get into the real content, I quickly want to acknowledge the team that I've been working with that has made Tessera possible over the course, especially of the past year, but especially over the past 3 years as well. So to give you a quick map for today, I will first be giving an introduction to foundation models broadly to make sure that we're on the same page. Second, I'll be presenting what came before Tessera, which is Spectral Temporal Barlow twins, and was also my early PhD work. I'll then talk about Tessera, how it differs. I'll finish with our findings so far, although most of that is available on our archive paper, and I'll finally conclude with what's next and then pass over to Daniel. So to begin, I first wanted to give you an introduction to foundation models to make sure we're on the same page. So foundation models essentially are built on self-supervised learning. And self-supervised learning is based on the premise that in many domains, we have a huge amount of unlabeled data. So you can imagine, for example, RGB images on the internet. Self-supervised learning functions by trying to sort all of this unlabeled data into a multidimensional space. So for example, let's say that our self-supervised learning algorithm creates a room, a box, and we want to sort images on the internet. This algorithm, for example, might put images of animals into one corner, of man-made objects into a second, and perhaps natural landscapes into a third. This model, this algorithm, will then export or output embedding locations as vectors of where all of these data points lie. However, these data points and these vectors are all relative to one another. And so to actually use these embeddings, we end up needing some labels, and we don't need many, to then contextualize this multidimensional space and make these embeddings useful downstream. Now, what might have caught your attention in the geospatial space is that we have, in our case, in our world, we have lots of situations with limited labels. As you all know, it's very expensive to collect labels. And besides this, we have tons of unlabeled data. We have petabytes and petabytes, for example, only of Landsat, and that's just one sensor. So if we think about our domain, the idea of self-supervised learning and by extent foundation models is a perfect fit. They're a perfect fit for each other, a perfect coupling. So we can think of now the input to the self-supervised learning as being geospatial data, really any of this unlabeled data that we have in the geospatial domain. We put this into our self-supervised learning algorithm. This outputs vector embeddings that, again, is identifying the location of our data in a multidimensional space. And then we can use our limited labels to then make the embeddings useful for downstream tasks. Now, when people talk about foundation models, this is a very loose term, and generally it's been used to talk about self-supervised learning that builds embeddings that can be used for many different downstream tasks. In the geospatial realm, sometimes people use foundation model to refer to models that can produce embeddings for an entire country, an entire region, perhaps the whole globe. However, this is a loose term, and it's built all on top of self-supervised learning. From now on, I'll use the term foundation model, but I want to be particular about where exactly the learning and model building is coming from. So now to transition, I want to tell you about what came before Tessera, Spectral Temporal Barlow twins, STBT. So Spectral Temporal Barlow twins was a predecessor of our foundation model, and it was really focused on agriculture, which is part of my personal domain background. In agriculture, we have lots of really complicated questions that we need to answer and that continue to be challenging today. For example, if we just take the case of a few grasses that we see often in Europe, we have wheat, we have barley, we have rye, and many other domesticated grasses that will all look very similar from space. So it's very difficult to separate these, let alone do other downstream tasks like yield estimation, etc. So my focus early on in my PhD was to develop a method that would be more useful for the agricultural space. And for this reason, I was specifically interested in pixel-wise multispectral time series data. What this means and the inherent belief behind this, and this is maybe one of the most important contributions that I can give you in this talk, is that there's an inherent belief in this that the temporal evolution of spectra is the most important component of this publicly available satellite data. So say like Sentinel-2 or Landsat, this is the most important component for understanding our agricultural landscapes. This contrasts with many different computer vision approaches which focus on spatial contextual information, perhaps as patches or as other spatial data being incorporated into the model. I want to give you one example that can help build this intuition. So I want you to imagine large industrial fields, for example, in Brazil or in the United States. Let's say it's a soy field. And if we go to the center of the field and we consider a pixel or a patch, we think about all the neighbors of this data, of the pixel or the patch. What we'll see is the same crop managed in the same way on the same soil. We'll have same. And so all that we get from looking at neighbors is that we're in a big field. That's all we'll get from incorporating all that extra data. I mean, there are other details. I'm simplifying, but this is to give you intuition. Now let's look at a smallholder agricultural context. For example, the Indian wheat belt. If we look at a small field that might be, say, 10 meters by 20 meters, and the pixel that we're looking at perfectly aligns with this field, if we look at neighbors, we'll probably get different crops and different management. It's a very discrete landscape. And so what we get at looking at neighbors largely is that we're in a smallholder context, or in a context where there's a lot of change. It's very discrete. But we already know this because we're looking in northern India, for example, and including that spatial information doesn't help much. So this is the background, again, of why we're focused on pixel-wise approaches, looking at the different spectra, and also looking at time series data. So given this background, we then were looking at architecture that would be compatible with this belief about the data landscape. And we identified Barlow twins. So how Barlow twins originally works is that it's built for the RGB images that we have all around us in the world. It works by intaking images one by one, and it creates two distortions of this image. There's then a twin pipeline where first an encoder works to take that image and compress it into a low dimensional vector. This vector is then expanded back out into what was called embeddings in the Barlow twins model, and these embeddings are pushed to be the same by the loss function. What this means is that the loss function works to widen the cross-correlation matrix between these two embeddings of the two different distorted images. What this is meant to do is to reduce the amount of information that the model is learning specifically about the distortions, and at the same time, make sure that the dimensions of the embeddings have very low correlation, so that each dimension of the embedding is as unique as possible, and as much unique information about the original image is encoded as possible. So this is what the loss function does. And that's basically the learning mechanism of Barlow twins. So if we think about this learning mechanism and we think about the geospatial context, a really easy interpretation would be to treat satellite imagery like RGB images. And we see this often in translations of computer vision approaches to the geospatial realm. So for example, we could take two patches of satellite image. In this case, I've shown a rotational augmentation, put that into Barlow twins, and then force the model to understand that these are the same. However, if we go back to the assumption and belief that I mentioned earlier, that the spectral and temporal information is the most important, we'll see that this isn't really compatible because it's prioritizing the spatial context and perhaps might only use RGB depending on how we design the architecture. So this simple interpretation or approach isn't really compatible with our beliefs about the world, especially when it comes to what's useful for agriculture. So building on this, how can we then reimagine the data to work with this particular architecture that we find so promising? So what we do is we organize the data in a slightly less conventional way, which we call the dpixel. How we do this is that we take the time series of a certain region, and for each pixel, we extract by time step the spectral bands from that pixel again. And we organize it in a two-dimensional array where you see on the right-hand side, we have observation dates or time steps as rows and spectra as columns. So now we have a two-dimensional array that is compatible with many of the models that are expecting some sort of multi-dimensional input like an RGB image, etc. So now that we're interpreting the data pixel-wise as temporal spectra evolution, we then can return back to the Barlow twins, and this is where our spectral temporal Barlow twins comes from. So if we take the time series, let's say it's for a year, and we have multiple dates where there's cloud cover, what we can do to create our two augmentations and what we consider to be natural augmentations is that we take a random subsample of dates, two separate times ordered. So we take a set of random dates, and then a second set of random dates. And we consider this to be two views of the same pixel, two different understandings of the same pixel, and we input that into the Barlow twins architecture, just like the images that were put in before. The model then, what it will learn in becoming invariant to our augmentations is that our model becomes invariant to the variations of dates available. So it's invariant to date availability. It's invariant to missing data due to cloud corruption. And so we're able to build a model that completely tolerates all of this, which is helpful, especially in the tropics, but all across the globe. Now, to be specific, exactly about what we're talking about when we do downstream tasks, Barlow twins, originally in this paper from 2021, it talks about the result of the encoder, the compression from the encoder as being the representation, and the result from the projector that the loss function acts on as being the embedding. However, in current dialogue around foundation models, we're usually talking about embedding being the thing that we do downstream tasks on. But this was not the language that was used in the Barlow twin paper, or that we inherited into spectral temporal Barlow twins in this early work. So when we're talking about downstream tasks, we're actually using what's called the representation, which is the compressed version, which we're compressing specifically to 128 dimensions. So what I've circled here, this step is what we use for the downstream applications of spectral temporal Barlow twins. So moving on, what we found in this prototype, this SSL prototype, this mini foundation model prototype, is that this approach compresses data quite significantly. So for example, if you imagine that you have 70 time steps in the year and that you have 10 spectral bands, that turns into 700 dimensions of data. If you put this into spectral temporal Barlow twins, what you get out is a 128 dimension vector. So great compression. Besides this, corruption from clouds is handled. We don't have to worry about missing dates. And besides this, when we actually looked at performance on downstream agricultural tasks, we found that using spectral temporal Barlow twins gave us equal or even better performance than using raw data methods or other SSL methods. So basically we found with STBT, great promise. And you can see this paper, it's available on JSTARS, and I'll also put the link in a bit, but this was a very early work. So we saw that there was a ton of promise when it came to spectral temporal Barlow twins, and that's what led us to then do work on Tessera. So this early work, like I mentioned, was my first PhD work. And then because we saw so much promise, we were able to expand the team by more than 10 people. And that's the team that's been working on what's now called Tessera over the past year, which has really been a fantastic project to be a part of. So what makes Tessera different than spectral temporal Barlow twins? So on premise, the assumptions are almost exactly the same. What changes now is that besides having our twin pipeline, our twin approach for the Sentinel-2 multispectral data, which you'll see on the top row, we also have now Sentinel-1 or SAR data, which is incorporated in a very similar way. So this data is taken as a D pixel once again to views our input into the model, into the encoder. But after the encoder step, the outputs from the Sentinel-1 and the Sentinel-2 twin siblings are glued together, and then those glued together versions are put into the projector, and we have the same acting loss function. So basically, this is just a way to now incorporate a second data modality into the pipeline that I already described to you. Besides this, we made our encoder slightly more complex. And after we did these architectural changes, we then had a vision to make Tessera be a global foundation model. And so Tessera, we ended up training on thousands of images from around the globe, Sentinel-1, Sentinel-2 images from around the globe, to create, ideally, annual embeddings of 128 dimensions for the entire global land surface. So that's our goal, and that was our vision when we started to train Tessera. And of course, this included a huge amount of infrastructure engineering work, a huge amount of engineering work. And I believe Daniel will be talking about some of the challenges when it comes to building out pipelines. But in general, this took a lot of time for us. So now I want to give you a little bit of intuition around Tessera. Here in this first example, I just want to show a visualization of the embeddings themselves. So this is of an agricultural region in Austria. And you can see that when we visualize just 3 dimensions of these embeddings, we already have very literally, but also figuratively, a colorful understanding of the landscape. We can already start to distinguish fields. We can see a riverine area, perhaps some conservation areas around this river, etc. So already we can see visually that a lot of information is encoded into the embeddings that we're getting out of Tessera that we can use to learn about the landscape. So In a few last minutes, I want to take some time to discuss some of the findings that we've seen so far. You'll be able to read about these, more about the task specifically in the paper. However, I want to walk you through a little bit of this to understand how Tessera exactly is performing. So the first example I'll give is for embeddings of a 2020 California fire. So this is a simple UMAP, so it's a unsupervised clustering of the data. And what we see is in the organic clusters that naturally exist in the data, we're seeing two really interesting things in this particular case. The first one is that although the embeddings are for an entire year, so they're encoding information from 1 year, 1 calendar year, we see that temporal information is still included. So embeddings that relate to an August fire event separate from a June fire event. That means that these event dates genuinely do separate in the embedding, even though it's for an entire year. The second thing that we observe is that within these fire events, particularly within the August fire event, we see a clear gradient between the low burned areas and the high burned areas, which means that this severity is also inherently coded. So this coloring was done after the UMAP clustering, but we can see that this naturally organizes into a space. Obviously, this is super simplified because it's 2 dimensions, but this gives you a sense of how we're seeing information being encoded into embeddings. A second example that I want to show you. Again, this is an unsupervised clustering of the data, then colored with land covers. This is for 2018 land cover in Senegal. So what we're seeing is a very clear separation of different land cover types. In this case, for example, cropland from shrubland, from wetland, water, bare soil, urban, built-up areas. We're seeing this clear differentiation naturally within the embedding. So we know that this information is being learned to be in different parts of our space, which is obviously exactly what we want and what we'd expect from Tessera. To give you another example, back to the forest space, this is Tessera used as an input to do canopy height estimation in Borneo. What you see on the far left is Tessera used as an input to predict canopy height. It has quite a good R-squared. You can see all of this. The second is Presto, the third is Google Alpha Earth, and the fourth is the composite Sentinel-2 product. So we can see that Tessera does quite well in estimating canopy height. Again, this is another example of what downstream tasks are possible using these embeddings. And fourth and finally, for the most complex task, this is crop type mapping in Austria. So even with a small number of labels used, this is on the x-axis to the far left, even with a very small percentage of labels used, we find that Tessera, when used as an input for crop type classification, still performs better than many of the other methods that would be considered. So what we have here are 2 different baselines that use raw data with different preparations. Those are the orange and red, and 2 other foundation models that are being currently tested for agriculture, which include Presto, which is in blue, and Google Alpha Earth, which is in green. You can see that Tessera, which is purple, performs above. So again, a very good result for Tessera. And broadly speaking, from all the work that's not in the paper as well, we've seen really incredible promise when it comes to what Tessera is actually capable of. And I really hope you'll consider using it. So to go over why consider using Tessera, why it's exciting, and this really goes for a lot of other foundation models as well, but what we're seeing with Tessera is that number one, like STBT, we're compressing the data. So an entire year worth of data of both Sentinel-1 and Sentinel-2 is being compressed into 128 dimensions. Secondly, corruption by clouds is handled. Third, there's no feature engineering needed. So for many applications, as I'm sure many of you know, oftentimes we do some sort of statistics across our imagery to make it better prepared to use for our modeling cases. This is no longer needed. As I would say in American English, it's very plug and play. Besides this, and related especially to the dimensionality reduction, we need significantly less compute to do any sort of downstream task because we obviously are working with much smaller data. Besides that, we're seeing the performance using Tessera is matching or beating other methods. And finally, big picture, we're working to pre-compute embeddings globally, which are becoming available via our GeoTessera Python package, which you can use by just putting in your region of interest, your geometry, to make effective. And I hope you'll try that out. So what's next? Big picture for Tessera. So like I've alluded to and I've mentioned, we have a paper currently on arXiv that describes the architecture in much greater detail than what I've been able to do today, as well as describe many of our downstream tasks. Besides this, we also have our entire model architecture on GitHub, which is available on our Tessera page at this QR code, but I'll also put the link in the chat. This is available, and also the pre-computed embeddings are available via our Python package called GeoTessera. This is also available on our GitHub. Any requests or questions you can send there. If you would like to join us in our mission of making Tessera great and usable for everybody, we're looking for about $500,000 US dollars, euros worth of support to pay for the compute needed to generate the embeddings from 2017 until today, as well as for storage space to store all these for everyone to access across the globe. So if you're interested, send us an email or contact us via GitHub. Big picture, we're seeing embeddings have huge potential. So putting Tessera aside, it's a really, really exciting time to be working on foundation models and with foundation models. And I'm really excited to see what all of us are going to be doing in this space in the coming years. So I will conclude. Thank you all so much, and especially thank you to GeoAwesome for hosting this event. And please feel free to contact me, like I said, at my personal email, since I'll be finishing my PhD shortly, or at our GitHub if you have any questions.